Okay, so now we're going to talk about something called fractional precipitation. Fractional precipitation is a way that we can use the solubility of materials to selectively pull different ions out of a solution. So if I have a contaminated water sample, for instance, it contains a bunch of different metals. I may have determined that through any number of other means. And I need to remove those metals from that water sample to make it safe to drink, for instance. There are ways that I can do that by precipitating out that metal. And that's by adding different ions to that particular solution so that we make the precipitate, we filter off the precipitate, and then we have one less thing in solution. So that's what fractional precipitation is about. When we talk about fractional precipitation, we selectively precipitate those ions from solution. Now, if the K values of the two ions that we're trying to precipitate are different, we can precipitate and remove one solid before we reach the conditions required to precipitate other ions. Okay? Careful setup for doing this will allow us to separate those ions. The ion with the smallest K precipitates first because it's the least soluble. So that's the one that's going to come out. We need to be able to describe this process, define what fractional precipitation means, and I want you to be able to use it to predict what order the ions will precipitate, or use it to choose a solution to use in such a precipitation and why you would want to use it. Okay. So for instance, a solution containing fluorine, sulfate, and carbonate ions needs to be separated. Given that BaF2, KSP 1.7 times 10 to the minus 6, BaSO4 has a KSP of 1.1 times 10 to the minus 10th, and BaCO3 has a KSP of 1.8 times 10 to the minus 8th, tell me the order of precipitation of those ions. Okay, so we're looking at precipitating all of these things with barium, right? So we're adding barium to this. We want to precipitate these ions in selectively. What's going to precipitate first? Well, which value of KSP is the smallest? And that value is the barium sulfate. It's 1.1 times 10 to the minus 10th. So that one will precipitate first. So if we're very careful about how much we add, and we're very close to that 1.1 times 10 to the minus 10th, we can selectively get all of the barium out. And then when we add additional barium to that, all of the sulfate out, and then when we add additional barium to it, then we'll start to precipitate the next ion, the one that has the middle solubility. Now, our middle solubility is that KSP 8.1 times 10 to the minus 9th. Okay, so that's roughly an order of magnitude bigger. So it's quite a bit different. So we should be able to manage that. Okay, once we've taken out all of the carbonate by precipitating that, then we can continue to add additional barium to that solution, and then we will precipitate the barium fluoride, BaF2, which has a KSP of 1.7 times 10 to the minus 6. Okay. So we go from least soluble to most soluble, and as we continue to add this is just like what we would see in a titration reaction, right? So if I had multiple acids in a particular solution, and I kept adding base to it, then I would get reaction of each acid as the K values came up, okay? Sulfate, then carbonate, then fluoride. Care must be used for sulfate and carbonate, and that's because if we go too fast, then we will not be able to get pure sulfate away from the carbonate. Okay? Those two values are close-ish, so we have to be careful about how we do that. So as long as we take care when we do it, we can make sure that that happens in a way that we can collect pure material if we need to. If we just want to get all of them out, and we just add a large excess of the barium, they all crash out. Okay? But typically, we want it to be fractionalized. We want to separate those ions from each other. Okay? So that's what we're talking about there. Questions, comments, problems on fractional precipitation? So hopefully not. But again, the practice that we're going to be looking at is what is the order based on these KSP values that these things would precipitate. One of the other things that we might be looking at is what would be a good choice to precipitate this metal versus another metal. And again, that's based on solubility for those things. So if we want to only precipitate one metal, we look for something that is going to create a precipitate with that metal and not with the other ones. Okay? So that's what we're talking about there. Now, hopefully that's good. So that's our fractional precipitation. And what is our next? The next thing we're going to talk about is pH. So I'm going to go ahead and pause here because pH is new. Well, no, actually I'm not. I'm just going to move into the pH instead of making this a new section. So other things that we can talk about in terms of what affects our solubility. pH can have a huge effect on what we see in terms of solubility. So if our substance has a basic anion, it will be more soluble in acidic solution. So that HF, right, if I have an F minus, that's part of that PbF2, and I want to drive that Pb into solution, then adding H to that solution pulls that HF out, and so that Pb will stay in solution. And it pulls the F out so that the F is back with the HF, and so that makes it easier for us to do that, okay? We don't see that same kind of effect when we talk about I minus because HI is a strong acid. So it works for HF, it does not work for HI. Remember that buffers control pH. When a buffer is used, there's no change in concentration of the hydroxide ion. And we'll see these calculations when we get to the common ion lecture. And the reason that we're not going to talk about them until we get to common ion is because we have a common ion that we have to deal with when we do this. So to talk about the mathematics, we need to introduce a new concept that is not part of this particular lecture, okay? So I'm not going to do that at this point, but I'm going to tell you that it's coming, all right? So factors, pH, changes in pH is a big way for us to change the solubility of these ions, okay? Now, amphoterism and solubility. Amphoteric oxides and hydroxides are soluble in strong acids or base because they can act as either an acid or a base, okay? So examples are oxides and hydroxides of aluminum, chromium, zinc, and tin. So if I have aluminum hydroxide and I want that to be more soluble than it is, I can add additional hydroxide. If I add additional hydroxide to that, I then form a complex where instead of being AlOH3, I'm AlOH4. And that is soluble. So that drives that solubility forward, right? Because the hydroxide pushes that towards that product, and that AlOH4 is soluble. Now, AlOH3 dissolves in strongly acidic solutions due to an acid-base reaction, okay? So if I add enough protons to this, that hydroxide that's on that Al all comes off. And so the aluminum becomes a soluble metal by itself without the hydroxide portion on it. So this is another way that we can use both pH and amphoterism, the ability to act as both an acid and a base, to change the solubility of things that we're trying to get into solution, if that's something that we need to do. Okay. So there are options that we have in doing that. All right. One last thing I want to talk about in terms of solubility. We don't talk very much about the solubility of gases. We typically only talk about the solubility of solids. But the solubility of a gas is proportional to the partial pressure of the gas above that solution, right? So if I have more of that gas above it, pushing down, it's going to go into solution more readily, right? Now, I'm never going to ask you to do a calculation with this, all right? But you might get asked if the solubility is higher at a higher pressure above the liquid. So I might say something like, I have this gas, like CO2, right? Carbon dioxide, that's above a solution of soda. And I pressurize that container that the soda is in. Is that CO2 going to be more or less soluble? And the answer is more, because the higher pressure means that it's going to push harder down. It's going to be more likely to stay in that solution. Okay, that is actually why sodas are overpressurized when you get them, is to try and keep that CO2 in solution. Okay, that ensures that it's carbonated when you get it. Okay, so that's what we're talking about there. Now, the equation is there. It's not that complicated, but we're not going to do any math. You just need to understand what we mean from a qualitative perspective, not a quantitative. So questions about that? Okay. Well, hopefully there are no questions about our end materials that we talked about there. I have one more thing that I'm going to be talking about, and that's the lab that goes with this. So I'm going to go ahead and stop here and set up for that discussion about the lab. All right. We'll talk to you soon.